This section we're going to take a look at section 8.8, which is improper integrals. And the first thing I want to remind you of is a definition or a notation that we've seen before. This is a notation that talks about having an integral from a to b of f of x dx. We call this a definite integral. And we're going to have that kind of an integration. It's going to look very similar to this, but we're going to have improper integrals, which means that one of two things is going to happen. Either one of those limits, a or b, is going to be either a negative infinity or infinity. In this case, we would use a limit to find the value of these improper integrals, and we'll do some like that. Or we would have a discontinuity within an interval, actually an interval a to b. And this happens when a and b are in the real number system. In other words, a or b can't be infinity in this discontinuities example that we're looking at, particularly in this case. So let's take a look at the first one. We've got an integral from 1 to infinity of 3 over x to the fifth. So the first thing that we're going to do is we're going to rewrite this with limits. So we're going to take this and we're going to call this the limit as b goes to infinity, because then I'll be able to write down the numbers from 1 to b, and I can also rewrite the 3 over x to the fifth as 3x to the negative fifth. And then I have methods we've done before on taking integration of a definite integral. So this would actually be 3x to the negative fourth over negative 4, evaluated at b and 1. We're going to plug the number b in, and actually we're going to also at the same time here, we're going to call this negative 3 over 4x to the fourth, so this will be 4b to the fourth. And then we're going to have a minus a negative, so this ends up being plus 3 over 4 times 1 to the fourth. Now clearly at the end here, this is the number 3/4. The issue at the beginning has to do with, as b goes to infinity, left that off, sorry about that, what happens to this function? You can do that in a couple of ways. You can either think about it analytically with numbers, so if I plugged in numbers that were increasingly larger in this particular denominator, I raise them to the fourth and multiply them by 4, and then I take them as a denominator and divide 3 by them, what happens? If I think about that perspective, that actually becomes 0. Or you can look at a graph, which is fine too, and if you take a look at the graph of this thing, it more or less is going to look like this. And the question is, as you move toward the right forever, because that's letting b go to infinity on this, what happens to the y values of this graph? And of course they level off at 0. So this ends up being 0 plus 3/4, which is 3/4, and we would say that this converges. All right, let's try another one. This one has the same kind of first of all setup. I have to rewrite this as a limit. So this is the limit as b goes to infinity of the integral from 4 to b of 1 over x times the natural log of x quantity cubed dx. And taking a look at this one, I think we're going to be able to use the u substitution to solve this. So u is going to be natural log of x, so that du ends up being 1 over x dx. And then I've got my limit as b goes to infinity. And because I'm changing this into a u substitution, I have to be really careful my limits of integration. I'm going to write down x equals 4 to x equals b. And then this would actually end up becoming 1 over u cubed, which is u to the negative 3 du. The du portion of it is the 1 over x and the dx, so those get replaced by du. Of course, the natural log of x is in the denominator, so the u cubed then would be in the denominator, which makes it u to the negative 3rd. All right, next thing we're going to do is we're going to integrate u to the negative 3rd, which is u to the negative 2nd. Let me write my limit first. U to the negative 2nd over negative 2. And then this needs to be evaluated back in for u, so I need to let x be what u be what x was, so I need to turn my u, in other words, back into ln of x. And looking at what I actually have, this is b goes to infinity. I actually have 1 over negative 2 natural log of x quantity squared, evaluated at b and 4. So limit as b goes to infinity of 1 over negative 2 natural log of b quantity squared minus, and then 1 over negative 2 natural log of 4 quantity squared. Alright, so again, we've got a natural log. We could think about this analytically. The natural log of b goes to infinity as b goes to infinity. If I take infinity as squared, it gets even larger, and then multiply by negative 2. It becomes negative, but it still gets increasingly larger in value. So this ends up being the number 0, because 1 divided by infinity, or 1 divided by something infinitely large, approaches 0. Then over here I have plus 1 over 2 natural log of 4 quantity squared. So my solution is actually this piece, 1 over 2 natural log of x quantity squared. All right, let's take a look at number 3. Now this one's different because I don't see an infinity or a negative infinity, but if I take a look at the numbers pretty quickly, I notice that I can't actually plug 0 in for this equation. If I plug in 0, I end up getting 10 over 0, and that's not a defined number. So when I do my limits on this one, what I'm going to do is I'm going to let my limit, and I'll call it a just because it's on the lower side, but it doesn't matter what you call it. Tell my limit to go from a equals, to take a to 0, and then we'll integrate this from a to 5 of 10 over x dx. Now, the integration for that, as you know, is a natural log. So this is a natural log. You can put absolute value signs if you'd like, but because this is going from 0 to 5, they're all positive anyway. So I'm just going to put the 8 in front and then natural log of x. We're evaluating this at 5 and at a. Okay, and then we have 8 ln 5 minus 8 ln a. There you go. Now, the natural log as a goes to 0. Let's just think about a graph of this thing. So the graph of natural log of x looks something like this. And if the x value is approaching 0, we're going downwards like this along the graph. And as you can see very quickly, this is actually negative infinity at the end. This is actually negative infinity times negative 8, which would be positive infinity. The first value, 8 ln 5, actually has a numerical value, but the infinity, of course, dominates. So this infinity is diverges. And even in writing that reminds me that I forgot to write converges on each of the other two. And again, the way you know is because if you actually get a numerical value, it converges. I guess I wrote on the first one. So the second one, you got a numerical value, so it converged. The third one, I did not get a numerical value. I got infinity, so it diverges. All right, somehow it looks like I turned my 10 into an 8 here as well. I'm sorry about that. Let me fix that real quick. It won't change my answer, but it'll just make this absolutely correct instead of looking odd, because that's what it looks like right now. Okay, those should have been 10s. All right, after that, I think we're good. So this actually diverges. Now we have one left to do. We're going to do the integral from 1 to infinity of 3 over x. And you might look at this and think, well, didn't we do one kind of like this already? You know, the first one we did, back over here, it was 1 to infinity of 3 over x to the 5th. And surely, whether the x is to the 5th or x is just by itself in the denominator, it seems like it should be the same. I mean, in fact, the graph looks almost identical. It's very, very similar, so what's going to happen here? They're not just the same thing. Well, in reality, it actually won't be the same thing, and if you take a look, you'll see why. And it's very similar to the last problem, part C, as to the why for this. So if I take this limit, or take this function and write the limit as b goes to infinity of the integral from 1 to b of 3 over x dx, then I have the limit as b goes to infinity, and I need to know the antiderivative of 3 over x, which is, of course, ln of x. And again, you could put in the absolute values if you'd like, but I'm dealing with numbers from 1 to infinity. They're already positive anyway. So this is from b back down to 1. So this is the limit as b goes to infinity of the natural log of b minus the natural log of 1. So natural log of b is actually going to be, and sort of in essence, taking a look at the graph of the natural log, which we looked at the left-hand side of the graph just a moment ago. Let's look at the right-hand side on this one. If x is going to, or b is going to infinity, we're moving outwards this way. And as you can see, this piece here turns into infinity. And then natural log of 1 actually happens to be 0, so we get minus 0, and my solution is infinity.